Thank you very much for inviting us here. It's an honor. I am Michele Samorani from University of Alberta.
I'm Linda LaGanga from the Mental Health Center of Denver.
Our project is about predicting if patients will show or not for appointments so we can optimally schedule them through overbooking. It's a work in progress. We are making progress. We will make more progress, but we're going to show what we have so far.
Okay. This work, actually, we've been looking at the problem of no-shows for quite some time. It's a well-known problem in clinical operations. We know we have this at our clinics. The clinics we're referring to are a community mental health center. We have about 35 locations and high number of no-shows. We are a large nonprofit, so we're really not focused on increasing profitability as much as what we really care about is being able to serve more people. So for us, the no-show problem is big because it reduces our effective capacity and means that often we have to turn away people who we really would like to be able to serve. So we really need to be able to utilize every bit of providers' time that we have. And just to give you an idea of the magnitude of the problem, we have had no-show rates on average as high as 36%. That's a lot of lost capacity. And we can't charge people for not showing because over half of our population is funded by Medicaid, and that's part of their rules and requirements. We have really worked hard to try to get that no-show rate down. People often ask, well, is overbooking the best approach? Couldn't you just figure out what causes no-shows and get rid of them? Yes, we do some of that. We have done work in that area. We've done some lean process improvement, and we have made progress. It's still about 25% on average across all our psychiatrists, and it varies between doctors. So there are differences within our system, and what we're trying to do with our analytics is use the information we have. The other advantage we have as a medical provider is we have a lot of data. We capture every activity, every appointment we schedule, whether people show up or not. We have all of that information in our database. So what can we do about it? Well, one thing that's really popular right now in outpatient services is using open access or same-day scheduling. Basically, the reason for doing that is it's well known, our data shows this, other studies have shown that the farther in advance you schedule, the higher the probability that you will have a no-show. So there have been lots of attempts to try to do shorter-term scheduling, even same-day scheduling. And you can see it right here in our data. If we schedule people the same day, they have an 87% chance of showing up. That drops off rapidly as you go further out, if you don't do anything else. But we'll talk about what we can and are doing about that. So the approach of open access or same-day scheduling is to not go out far, to only give people same or next-day appointments. The problem with that is you've got a lot of variability still in your system, and you don't know exactly how many people are going to be seeking appointments in any given day. And the other problem is when you run out of capacity, you run out. Very often people are told to call back, which they do repeatedly, which really just adds to the non-value added part of your workload, handling calls for people who you're just saying no to anyway. So it's not necessarily the best approach. Other approaches that we've been considering, back in 2007, Steve Lawrence and I started doing work on no-shows and overbooking. Basically what we were looking at was whether one should or should not overbook. The obvious advantage of overbooking is you will, on average, see more patients. That's the good thing. The bad thing is you will build up more patient wait time, and you will run the risk of sending your providers into overtime. So the way it works, if typical appointments take a half hour, usually what clinics do is schedule them every half hour. The problem is when you have no-shows, you end up with half-hour empty blocks that are not utilized with regular scheduling. What we've done with our initial approach was to compress those appointment slots as a way of making more of them without having to double book. That's how we started off. So instead of scheduling every 30 minutes, we just shortened that inter-arrival time to every 20 minutes. Again, though, some fall out. The problem with that kind of overbooking, even though we think the compression was a helpful way of sharing the load of patient wait time and provider overtime, it doesn't take into account that different patients might have different no-show rates. And we really had no other information about which ones were likely to show or not show. Depending on those patterns of when they show up or don't show up, that's how you incur patient wait time and provider overtime. So this one, by luck of the draw, would be considered a pretty lucky case because you have spaces in between where people don't show up, which allows you to catch up in your schedule. Meaning we were able to say yes to people. They ended up not showing up, but overall we can operate pretty well. Patients don't have to wait. We don't go into overtime the way the appointments end up being filled. Now, the other thing that can and does happen without further information is unlucky overbooking, where we squeezed more in. In this case, if the first few of them didn't show up, you would have providers sitting idle throughout much of the morning, and then all your patients arrive in a row. So those patients get backlogged, they end up having wait time in the clinic, and your providers end up having overtime. Not your best case. This is the problem that we're trying to solve.
So let's try to schedule them using analytics. When an appointment request arrives, we use a classifier to predict if that person is going to show or not for all day in the scheduling horizon. And then we're going to use this prediction to optimally schedule them in a certain day and slot. So for example, suppose that the current schedule is this. We have a few patients already scheduled. Some are predicted to show, and one is predicted not to show. We have a scheduling horizon of 3 days, which means in this small example that we are allowed to schedule patients only today, tomorrow, or the day after tomorrow. So this appointment request arrives, and you see it gets 3 predictions, one for each day. In this case, this patient is predicted to show on day 1, 0 today, tomorrow, but not the day after tomorrow. Why is the show probability dependent on the day? There are many reasons, all documented in the literature. Lead time, personal schedule, the day of the week, the weather, these are all day-dependent factors. Now, we solve the scheduling problem with this objective. We want to maximize the number of shows. So, for example, we are tempted to schedule this person in day 0 or 1, where it's predicted to show. But we want also to minimize waiting time and overtime. And in this case, for example, we schedule him there. Okay, this is the overview. Now, what are the goals? We want to understand the causes of no-shows. We want to obviously accurately predict the show outcomes of the appointments. We want to optimally schedule appointments. Then we have some constraints. We want that the scheduling policy to be practical. We want that the scheduling algorithm makes sense. That's because they want to have a feeling for it. And then we want to provide guidelines about the clinic design, and I'm going to discuss that later. So let's talk about the classification rule and how we find the causes of no-shows. So as you all know, when you use any data mining machine learning algorithm, you require a mining table. I call it mining table. You can call it input table or whatever you want. A table that in this case has 1 row per appointment, of course, 1 attribute for each attribute, and 1 extra attribute, which is the show outcome, whether that appointment resulted in a show or not. Usually, a table like this is built manually in the sense that in collaboration with the mental health center, I would try to understand what attributes they feel are more interesting or they suspect they are linked to no-shows, and then we would include them. But in that case, we would include actually already attributes that they think they have something to do with no-shows. So we wouldn't really find new knowledge, maybe. By contrast, we build this table automatically through an algorithm called Propositionalization. This is the database of the mental health center. They have, of course, a table with appointments. Each appointment has 1 client. each client can have had many appointments. Each client has a series of assessments made by the provider in terms of housing, employment, and then there is a staff for each appointment. We want to add attributes to the table appointment. This is our mining table, but it has few attributes. We want to bring information from the other tables to here automatically. I'm just going to show an example. I'm not going to go into too many details. So to generate an attribute, you pick a path starting from appointment. So for example, the path appointment, staff, appointment, client. And then you roll up attributes starting from the last arc, and you aggregate information. So for example, each appointment can be, we can virtually add the age of the client to that appointment. Then we go back to the previous arc, staff to appointment. Each staff has many appointments, so we can virtually add to staff the average age of the clients, and for example, seen in location L. We also add a filter. You can add any filter you want. Finally, we add this attribute to the table appointment. The average age of the client seen by the staff in location L. And we do this automatically. So does this attribute have anything to do with no-shows? Probably not. Probably this has nothing to do with no-shows. But since you generate a lot of attributes, you generate 3,000 attributes, that's what we did in 3 hours. Many of them have nothing to do with no-shows, but those that do have something to do with no-shows, they represent new knowledge. And Linda is going to talk about this.
Right. So over the course of many of our managers, directors, even therapists have been around for a while. They have really good intuition. There are some things they do know and understand about no-show rates, even without looking at data, although we look at the data as well. So what things make a difference? Well, we do know the further you schedule people out, that has a big effect. Location. We know that there are some teams, clinics, types of services that have higher or lower no-show rates. Previous no-show rate. We know that a person's past history of whether they'll show up or not is a really good predictor of what they'll do in the future. So these are not surprising that these are discriminant. We expect that. Some of the things, though, that we didn't really think about because there's so much data and so many combinations that I constantly tell my colleagues, wow, Michele's always telling me new things that we really didn't know before. Things like how many times a staff member has performed group therapy. I wouldn't have thought of running a report to look at that. But now that we know it, it makes sense. These are people who are more experienced. There often are reasons why things about the staff make a difference with no-shows. Number of times they performed case management. That may say something about the provider's practice style, what types of services they deliver. Number of times that staff member has been in a certain location. It's a complicated system we have. So we do have staff who end up in different places. That's one, again, I wouldn't have thought of specifically drilling down on the data and looking at that. So that's been very helpful, particularly because it's unexpected, but it really makes a difference in predicting who's going to show or not.
Thanks. So what is the prediction quality? We found new information, but what is the prediction quality we achieve? Here, it is more important to keep track of the sensitivity and specificity of the classification rule, not much the accuracy. Sensitivity is the accuracy among the non-showing appointment requests, and specificity, the accuracy among the showing appointment requests. Note that by using cost-sensitive classification, which is a well-known classification framework, we can shift the prediction quality towards maximizing sensitivity or specificity. And this, I'm going to show, will result in actually giving different weights to our two objectives of maximizing shows and minimizing overtime and waiting time. These are conflicting objectives. We obtain, of course, I'm skipping a lot of details. We separated in the data set into training set, test set. But at the end of the day, we obtain any of these three classification accuracies. And by using cost-sensitive classification, we can actually move throughout that performance frontier. We are using Bayesian network, by the way. We tried all possible classifiers we had. That is the one that performs best. Of course, we would like to be in the 1 cell, the upper bound of the prediction, where we can predict everything. And we don't want to be in the lower bound cells, the random predictions. Okay, so now that we have our prediction, how do we use it to optimally schedule an appointment? I'm not going to go into too much details, but we have a mathematical model which is rather complicated and relies on generating scenarios of possible future arrival appointment requests. And it also supports categories for waiting time and day and patient-dependent revenues and other characteristics. We solve it via column generation. In the model, you can see that the column variables are these y's. But I'm not going to talk much about it. Why not? Because they want something interpretable, and this they don't like it. I mean, we can implement it, of course, but they want to have something that when it outputs at day and slot, it makes sense to them. So can we get there? How can we have the scheduling algorithm interpretable? Well, we're going to use analytics. We're going to embed the optimization algorithm, that hard, uninterpretable one, in a simulation framework, and every time it makes a decision, we log it, and then we mine this data set of decisions to make sense of them. In particular, we use association rules and found that, for example, if the predicted show outcome is no-show, then schedule the appointment in slot 3 or 6. If it's show, then schedule the appointment in other slots. This, again, is a summary of rules. It was not that easy. But yeah. So what these summarized rules mean is that in this small case, we are trying to achieve this target sequence. We want a show, show, no show, 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 no show. Why is that? Well, it makes sense. In this case, we have capacity 4, but we schedule 6 appointments. Of course, we want the last one to be a no-show because we want to avoid overtime. So if you have to have a no-show, put it there. And the other one, well, in the middle, so to avoid build-up of waiting time. Interestingly, a further analysis reveals that no-shows tend to be scheduled far in advance, and shows tend to be scheduled in the near future. Why is that? It's because, of course, it's easier. So, in other words, it makes sense if you are overbooking, you want some no-shows in this slot. So to make it happen, to make sure it's a no-show, you schedule those slots very far in advance to people that are already likely to be no-shows. Scheduling them far in advance will make almost sure that they will actually not show. On the other hand, the show slots, you schedule them at the last moment. That is, of course, what the mathematics behind the algorithm says. Now, it may be not completely ethical, but we don't have to use exactly this. This gives the idea of what we want to achieve. Of course, there are exceptions, right?
And the flip side, from a treatment point of view, is you want people who are really ready for treatment. You really want to help them come in. So it makes it more likely that they will show up and that we actually can serve those people who are most likely to benefit from treatment sooner. And the others, they may still be contemplating whether they're going to show or not, but at least they're not calling you every day seeking an appointment that they're not likely to use anyway.
Right. So our heuristic is schedule the predicted shows soon in show slots and the predicted no-shows far into the future in n slots. And this, in our experiments, achieve a profit that compared to the optimal is just 2.1% lower. So that's very good, actually. Okay, so it turns out that, as we could expect, if we increase the sensitivity, and of course we can do it in simulation because we know the real class of everybody, the profit, these bars and labels, increase. That is not surprising. However, as you can see, the number of patients seen increases, and so does the overtime. With specificity, the same thing seems to happen, but differently. The profit increases with specificity increasing, unsurprising, but the number of patients seen remains more or less constant, and what decreases is the overtime. This shows that sensitivity and specificity regulate the trade-off between the two conflicting objectives of maximizing patient seen, that if you want to give an incentive to this objective, raise the sensitivity, and minimizing overtime and waiting time. Even more interestingly, if we increase the scheduling horizon, we achieve a higher profit only if our sensitivity is high. Look at the light gray bar. That, unlike the others, decreases, which means that if we have a bad accuracy, bad sensitivity in this case, the best option is same-day scheduling. And the same pattern, we see it on specificity. This is simply amazing because same-day scheduling is considered one of the leading, most popular techniques to avoid no-shows. We prove that, yes, it's the best only if you're not using predictive analytics. Because if your prediction quality is decent, then you should have a longer scheduling horizon because you have more freedom. Same-day scheduling is worst if prediction is high, quality is high. We also compared it to open access, in particular the implementation of Robinson and Chen, who suggest to limit the appointments to same or next day scheduling. We use our heuristic, and parameters of our heuristic are the sensitivity and specificity, because of course we can more or less manipulate them. Well, it turns out that the highest profit, we achieve it with the high sensitivity classifier. We beat open access by 18%, which is really remarkable. Interestingly, even the lower bound is higher than open access. But that's lower bound, what does it mean? Just basically almost randomly scheduled appointments. But that's only true if the show rate is as low as the one we observe. If they manage to increase the show rate by using their policies, such as reminder calls and engaging patient better, what is going to happen? The first point here is what you saw in the table of the previous slide. We have open access, then the lower bound, heuristic, and the upper bound up there. If we manage to increase the same day and next day show rates, and you can see this, we can artificially pretend that they are higher. Heuristic is always a little better than open access. The advantage decreases. Lower bound, just don't use it unless, of course, everybody shows up, then, which is this case. Then everything more or less performs similarly. And this thick black line, heuristic, is actually the maximum among our three combinations. If you actually explode that, you see that the high sensitivity classifier is the one that performs best for low show rate. The high specificity classifier here is the one that performs best for high show rate. And why is that? Because when you have low show rate, your priority is increasing the shows, and that is done well by the high sensitivity classifier. When you have a very high show rate, what you want to do is recognizing the no-shows so that you can put them strategically to obtain a good overbooking. Okay, we can see also that the waiting time frequency, if we use our heuristic, we tend to obtain more frequently low waiting times and also low overtimes. If you don't use analytics, it may happen very often that you go overtime by hours. And that doesn't happen if you use analytics. This is really remarkable. So in conclusions, we find the causes of no-shows, develop a dynamic scheduling algorithm, heuristic that is interpretable and easy to implement. We outperform open access. We reduce system variability, as you saw from the last charts. We think we contribute to all three areas of analytics. We show that propositionalization is a good way to find new knowledge. We show that cost-sensitive classification can be used to favor one of conflicting objectives. We suggest when to lean towards sensitivity or specificity, depending on the situation. And we also interestingly studied the output of optimization using analytics in order to find a heuristic. I'm going to let Linda talk about the current progress. That's our last slide.
Right. So this is currently in progress. One of the big breakthroughs we made was that I mentioned we have an electronic medical record system. It's used for all our scheduling, tracking and recording all our services. We've actually got it up and running so that Michele's software actually can communicate with our medical record system. That's a big breakthrough because it actually enables the front desk staff who are doing the scheduling to use this information which can help them build better schedules. So that was a huge breakthrough. And with that, we've been able to run this in the background and observe how good are these predictions. And Michele showed you the results of that. The predictions do support making better decisions than we would make without it, just doing open access. So second phase, we just moved, we consolidated several clinics. We now have them all together in one place, so we're ready to get back on board with, we had a doctor who has volunteered to pilot test this for us, so to actually start doing some overbooking there, because the psychiatrists actually do want to boost their productivity, so they're highly motivated to find better ways to schedule so that their boss won't be bothering them so much for, why aren't you seeing enough patients? So,
thank you.
Thank you.